The derivative of a natural log of x is 1 over x. And we can show that very easily, assuming that y is equal to the natural log of x. So we're just going to prove this derivative very quickly. If y is equal to the natural log of x, writing that in exponential form, it would be e to the y equals x. Now, differentiating this, you would have to differentiate implicitly with respect to x. So this would be the derivative with respect to x of e to the y is equal to the derivative with respect to x of x. So just differentiating each side and simplifying, this is e to the y multiplied by the derivative of y. That's your implicit differentiation. And the derivative of x is 1. Now, solving for the derivative of y with respect to x is equal to 1 over e to the y. 1 over e to the y, well, we know e to the y is x, so this is 1 over x. And right there we have shown that the derivative of y with respect to x is equal to 1 over x. This formula is something you should circle, star, and highlight. You will use that all the time. It needs to be in your brain. The derivative of a natural log of x is 1 over x. This will be pretty easy as long as you know the definition of the derivative of a natural log function and also the chain rule. We'll use a u substitution in this case. So if I let u equal x cubed plus 1, if u is x cubed plus 1, we can go ahead and simplify this. So the derivative of y with respect to x, and using the chain rule, it would be the derivative of y with respect to u multiplied by the derivative of u with respect to x. That's the chain rule. Now, derivative of y with respect to u. So writing y in terms of u, our u substitution, y is equal to the natural log of u. The derivative of y with respect to u is 1 over u. That's the definition that we have. Multiplied by the derivative of u with respect to x, which would be 3x squared. Simplifying there, we can substitute back in our u and simplify. So this is 3x squared over x cubed plus 1. And that is our derivative. Looking at that example that we just went through, you can kind of generalize this when you have natural log of a function. You can see that the numerator is the derivative of the inside. So if I have a function that is y equals the natural log of some function, the derivative y prime will always be the derivative of the inside, g prime of x, divided by the inside function, g of x. That's a quick and simple shortcut for our natural log derivative. Another example for the derivative of a natural log function. Let's go ahead and use that generalized formula that we had before. Stating it again, it was the derivative of the function that is a natural log will be the derivative of the inside over the inside function. And like I said, you'll get the same exact answer if you use the chain rule. So, showing that, we know that this is equal to the derivative of sine, which is cosine, over the inside function, sine. Using your trig identities, cosine over sine is cotangent. This would be our derivative. Looking at another example, we'll take the derivative, or find the derivative, of the square root of the natural log of x. Using our rational exponent property, we know that this is the same as the derivative with respect to x of the natural log of x to the 1/2 power. Using this fact, now we can use the power rule along with the chain rule, since there's the function inside of a function, and differentiate. So it would be 1/2 natural log of x to the negative 1/2 power. And then we need to multiply it by the derivative of the inside using the chain rule. So it's multiplied by the derivative of the natural log of x, which we know is 1 over x. Simplifying from there, we know that this is 1 over 2 square root of natural log of x multiplied by 1 over x, which is the same as 1 over 2x square root of the natural log of x. And that is our derivative of the square root of the natural log of x. For our next example, we're going to take a look at finding an absolute minimum of a function. So we're going to be going back and bringing back all of the things that we've done for quite a while with derivatives and first derivative tests to find maximums or minimums. The new part is we're actually going to apply the differentiation formulas for the natural log of x. So let's go ahead, and if we want to find an absolute minimum, or maximum for that matter, we need to find the derivative and then set it equal to 0 to find critical points. F prime of x is equal to, now this is a product, so we'll use the product rule. First, multiplied by the derivative of the second plus second multiplied by the derivative of the first. Here's our product rule. We'll simplify that a little bit to make our life a little easier. That will simplify to be x plus 2x natural log of x. This is our derivative. Now, we can factor an x out to make this just a little bit easier. 1 plus 2 natural log of x. This is our derivative. To find critical points, we set f prime of x equal to 0. So, 0, we have x, 1 plus 2 natural log of x. Setting each factor equal to 0, and then we'll solve. So x equals 0, x equals 1 plus 2 natural log of x. 0 is the one we'll talk about first. This is actually not in the domain of our original function. So there is definitely not a critical point at this value because I cannot take the natural log of 0. It has to be a positive value in order to apply the natural log. So this solution is not part of the original domain, therefore it is not a critical point. For our other value, having it equal to 0, we will solve this value. It will be negative 1 is equal to 2 natural log of x. Negative 1 over 2 equals the natural log of x. And when I want to solve a natural log or a log function for x, you have to write it in exponential form. So I need to get x by itself. This will be e to the negative 1/2 equals x. This is our critical point. We will check for a sign change here in just a second. So that value, if I write it over here, e to the negative 1/2 is x equals 1 over e to the 1/2, or 1 over the square root of e. That is the value that we'll place on the number line. Placing it on the number line, 1 over square root of e. We know that we cannot have a number less than 0. So I have to pick a number between 0 and 1 over the square root of e. This value, 1 over the square root of e, is a positive number because e is about 2.71-ish. So the square root of that is going to be a number that is positive. It's going to be greater than 1 but less than 2. So we know that we need to pick a value. If I pick a value of 1/2, we'll probably be fine. When you plug that value in, you're going to find that that is a negative value. And when you pick a number greater than 1 over the square root of e, you will find that it's a positive value. So this is my derivative sign. So that means about the original function that it's decreasing and then increasing. If we have a decrease, then an increase, we must have a minimum value at that point. So our minimum value occurs when x is equal to 1 over the square root of e. That is our x value. If we wanted to find the actual minimum value, the y coordinate, you would plug this into the original function and solve. And that would be our minimum. Suppose we're given the natural log of x plus 1 over the square root of x minus 2. We can differentiate this in a couple of different ways. The first way is using the rule that we talked about a little while ago of the inside function's derivative over the inside function itself. That would give us y prime when you have a natural log function. That's the shortcut. Or you can use the chain rule, which is the same exact thing, really. If I differentiate this that way, we will have the inside function's derivative. So you'll have to find the derivative of x plus 1 over square root of x minus 2 and divide that by the original function, x plus 1 over the square root of x minus 2. This will give you the derivative. Now, when you differentiate this value, you notice you're going to have to use the quotient rule. So make sure you apply quotient rule here, and I'm going to leave that one for you to do. Another way that you could go ahead and find the derivative is use your properties of natural logs. If I know that this is division, we can separate that or expand the natural log to be the natural log of x plus 1 minus the natural log of the square root of x minus 2. You can differentiate this since it's the same thing. Going a little further, we know that it's the natural log of x plus 1 minus 1/2 the natural log of x minus 2. Just simplifying using that power rule for a logarithm. Now, when you differentiate this, you can differentiate each of these pieces separately and keep the subtraction in the middle using your derivative rules. This way will probably be a much easier way than this. So the moral of the story here is make sure you try to simplify this inside function or the logarithm itself first and then differentiate, and you could save yourself a lot of time. Either way, you'll get the same answer, and I'll give you the answer and see if you can come up with it. It should. The derivative of y will end up equaling x minus 5 over 2x plus 1 x minus 2. This should be your answer after you differentiate either one of these, choosing your favorite. This new derivative rule that we have just learned about will help you greatly when we're finding antiderivatives of 1 over x. Now, antiderivatives, the indefinite integral, will undo what the derivative does. So we know if I'm anti-differentiating 1 over x, the answer will be the natural log of the absolute value of x plus c. Now that saves your life because we have ran into this a couple of times where we have 1 over x and you try to anti-differentiate. We know this is x to the negative 1. And when you use your normal rules for anti-differentiation here, you add 1 and then divide by that number. So it would be x to the 0 over 0 plus c. And that we know and have run into this problem, that is a horrible, horrible idea. This does not work for the antiderivative of 1 over x. This is your antiderivative. And now that we know that, we'll go ahead and start using this value for our antiderivative of 1 over x. This saves our life now, and we will no longer explode when we try to divide by 0. For the next example, we're going to find the area under the hyperbola xy equals 1 from 1 to 2. And we'll find that using a calculator correct to 3 decimal places, obviously. In order to do so, I'm going to solve this for y. Now I see I have 1 over x. Fine, fantastic in fact. And we want area under the curve from 1 to 2. That tells me instantly we're going to be using a definite integral. The area under the curve will be the definite integral from 1 to 2 of 1 over x dx. Now using what you have just learned, you can now anti-differentiate this. So we can find the antiderivative, and you know using the fundamental theorem of calculus that this, the natural log of the absolute value of x, evaluated from 1 to 2. Now, we can go ahead and use the fundamental theorem of calculus here and say that this is the natural log of 2 minus the natural log of 1. And that is something that you would type in the calculator and get an answer. I believe the answer should be about 0.693. That is correct to 3 decimal places. Area under the curve. For our next example, we're going to find the antiderivative of x over x squared plus 1. So, finding this value, I'm going to use a u substitution, and I'm going to rewrite this quickly here. It will be 1 over x squared plus 1 multiplied by x dx. Now, using a u substitution, if I let my u be x squared plus 1, then du is equal to 2x dx. We know that du is equal to 2x dx, or 1/2 du is equal to x dx. That value right there is important because I see it over here. So putting it now in terms of u, this is the same as 1 over the antiderivative, or the indefinite integral, of 1 over u du, as long as I have my 1/2, which I'm going to take out front. It's a constant, you can take it out front. Now, anti-differentiating here, we know that this is the same as 1/2 multiplied by the natural log of the absolute value of u plus c. Then all we need to do is plug back in our u value, which is 1/2 the natural log of x squared plus 1 plus c. Here is our indefinite integral, or the antiderivative of x over x squared plus 1.